The PAWS device is an audio visualization project which enables users to perform fast Fourier transform analysis on any given audio signal using a portable device. The device, such as an iPhone, pairs with an integrated app that offers integration with the Spotify API, giving access to the entire song bank within Spotify, in addition to any other sounds desired to be played through the iPhone. Using a Bluetooth connection to a Raspberry Pi, the user can select between various visualization modes. Our device is designed for long battery life, ranging from 8 to 14 hours of usage. Again, all of this resides in a portable boombox configuration for ease of transportation and avoiding any connection difficulties.
Our system is enabled by a 12-volt and 5-volt dual voltage system. This dual voltage system is supplied through a single voltage source, which allows us to avoid any potential grounding issues. Our 12-volt source primarily powers a Class D audio amplifier supplied by Adafruit, which powers our 30-watt speakers which produce our sound. In parallel with this 12-volt source, we also have a voltage detector, which essentially allows us to monitor our battery capacity at all times. In addition to this 12-volt source, we have the 5-volt source, which is connected to both our Raspberry Pi and any peripherals that might connect into the Raspberry Pi. This includes a I2C enabled rotary encoder, which allows us to change the volume digitally as opposed to using analog method, which would require a potentiometer. In addition to this, we also have a matrix hat, which supplies both power to the LED matrix as well as decodes output signal from the Raspberry Pi and sends that to the LED matrix so that we might be able to display anything that we might prefer. The switching of these two voltage sources is enabled by two PMOS transistors. And those transistors, by the push of a button, switch the 12-volt to the 5-volt respectively. Lastly, we have an analog to digital converter externally connected to the Raspberry Pi. The power to this analog to digital converter is connected to the 3.3 volt output on the Raspberry Pi so that the analog to digital converter turns on and off when the Raspberry Pi is turned on and off to keep our signal continuous.
When you open the app, you're greeted with a welcome page and soon move to a Spotify login button. Here, we log into Spotify, agreeing to their terms, and you're directed back to the PAWS app. From there, you connect to the Bluetooth speaker, which I've already done, and you're done with our setup. Next, you can move in, look at your playlists. From there, you have many options to choose, as all of your Spotify preferences are saved and transported over into our app. You can also search songs that you haven't yet used. Here we search John Mayer and can control what's being played on the speaker. We also have the ability to change modes. Here I change to rainbow. As you can see, all the LEDs are lit up. Next, we're a pink time, so this is the time domain of our song. Here's a fast FFT. This refreshes very quickly. We also have a text mode. Here, our team name is being displayed. I also have the ability to create new modes. Here I'm creating a green FFT. This is going to be a slow one. And I switch to that mode here. Once these modes are created, I also have the ability to edit the mode. I'm going to change the color to orange. Go Tigers.
This clip will demonstrate the accuracy and frequency range of our visualizer. As you can see, there is a 100 Hz sine wave currently being played through the system. The mode that we are in takes the average of 7 FFT graphs, then prints the average result. As we move to the 200 Hz sine wave, we expect the graph to peak around the middle of the matrix, as we have the ability to display a range from 0 Hz to 460 Hz, because our Nyquist rate is 920 Hz. We choose to use this average FFT mode in this demonstration to allow for more precise data to be shown compared to the rapidly refreshing FFT. Through this test of 4 frequency ranges, we find that our matrix displays the data correctly without any error.
This next representation is showing our different modes of fast Fourier transforms. So as you can see, there is a consistent frequency of 200 Hz being shown, and that is being shown in both the frequency domain and the time domain as shown here. The color and the rate of the Fourier transform can be shown. So the fast Fourier transform is without the averaging, whereas a slow Fourier transform includes the averaging we alluded to earlier.
Let's dive a little bit deeper into the software of our app. How does the Bluetooth work? So we're using Bluetooth LE, also known as Bluetooth Low Energy. This connection is typically used for passing data rather than audio. For audio, we are using Bluetooth Classic. So we do have 2 Bluetooth connections going on simultaneously to communicate with our device. One being Bluetooth Classic for all music-related data, the other being Bluetooth LE. The Bluetooth LE connection, we actually did have to develop a little bit further. We made this a UART connection, so there's a UART bus that the Pi and the phone or connected device can communicate on. And this we are using just to update. We pass a live string, which conforms to our protocol. And our Pi knows how to interact and interpret this data. And as you can see on my phone, if I change rainbow, it knows that mode 2 is rainbow. If I go up to a blue slow FFT, you can see clearly that the color is changing and the mode is actually changing as well. I can also go and directly input a text message, update the new message, and I can send that message. And as you can see, a new message is displayed when a new message is prompted. Color changes are also able to be done on the fly in this mode, and all of this is handled through the UART bus. This bus was developed using read and write characteristics. These characteristics can work both ways, so if the Pi were to die or we wanted to add a battery on the phone in the future, we could actually write to the phone and update with new data from the Pi. And this is something that we looked into, but due to time constraints was unable to fulfill.
The first flight of the earlier discovery, and the shuttle has cleared the tower.
After roughly 750 hours put into this project, we have produced a robust, complex, and most importantly, functional portable audio visualizer. We are proud that we are able to overcome learning and utilizing new skills, including coding in Python, fully developing an iPhone app, functionally implementing the Spotify API, creating a dual voltage power supply, and constructing a system with many new kinds of hardware, such as the LED matrix, Raspberry Pi, and analog to digital converter. We are grateful to the Clemson Electrical and Computer Engineering Department for their resources and financial aid, which allowed us to succeed and explore the world of integrated systems design.